Welcome everyone. I'm Georgios Rigas from Imperial College London and member of the editorial board of PRF. It is my pleasure today to moderate the PRF Journal Club. And today's talk covers the recently accepted PRF letter specifically, mechanism of stochastic resonance in viscoelastic channel flow. This work will be presented by Yuke at Harbin University. And this has been done in collaboration as well with Victor Steinberg, Weizmann Institute of Science. Before we begin, a quick reminder, the presentation is 15 minutes and it will be followed by 15 minutes of Q&A. Please hold your questions until after the talk. And during Q&A, you can either raise your hand in the Zoom application here to ask orally your question, or you can post it in the chat. And during the talk, please keep your microphones muted. Without further ado, I'm going to give the floor to Yuke for his presentation.
Okay, thank you. Thanks for Georgios' introduction. Hello, everyone. This is Yuke, an associate professor from Harbin Engineering University. I worked with Professor Victor Steinberg at the Weizmann Institute of Science when I was a postdoc, and we are still continuing to collaborate. I'm very glad to have this opportunity to share our recently published paper in Physical Review of Fluids. I also would like to thank the PRF Journal Club Committee for the kind invitation and their efforts for organizing this event. This paper originally builds on our earlier discovery published in Physical Review Research and focuses on the mechanism of the stochastic resonance, SR for short, especially how SR merges and exists in inertialess channel flow of polymer solutions. First, let me introduce elastic turbulence. Elastic turbulence is a chaotic flow state driven purely by the elasticity of dissolved polymer, usually at very low inertia, with Reynolds number much smaller than 1. The first experiments was characterizing elastic turbulence were conducted by Victor at the beginning of this century. Before going further, some important dimensionless number should be introduced. The Reynolds number, the initial effect to viscous effect, the Weizmann number, reaction time of polymer to the hydrodynamic characteristic time, which quantifies elasticity, and the elastic number, the Weizmann number over Reynolds number, and the last one is the viscous ratio, beta. When beta equals 0, the fluid behaves like a pure polymeric mat. When beta equals 1, it is a purely Newtonian fluid. The classic linear instability of inertialess polymer solution flows with curved stream lengths is driven by the hoop stress mechanism associated with the most unstable non-asymmetric mode. Because the two ends of the polymer chain will experience different velocity gradients, this creates a non-zero first thermal stress difference. However, this mechanism becomes insufficient in zero curvature limit, such as parallel shear flows. Therefore, the first impression one might have about viscoelastic channel flow at low inertia is that strong enough perturbations are needed to trigger elastic instability at least. In our earlier work, we tested several inlet configurations, an array of obstacles at the inlet. Second, a natural abrupt inlet with pressure measurements holes on downstream, and the last is a smooth converging inlet. We found instability in all these cases, but with different critical Weizmann number, although they have the same cross-section dimension. From the friction fraction measurement, velocity spectrum, and strict evolution, we observed a direct transition from laminar to chaotic flow without an intermediate state. This contradicted the scenario in the linear instability. The direct transition is confirmed by a recent numerical simulation in three-dimensional channel flow. we concluded the transition is due to the non-normal modes. In addition, we discovered a special phenomenon, elastic waves, as shown in the span-wise velocity spectrum on the upper right corner, EW. A distinct spectrum peak emerges as the first signature of the elastic wave intensity. We found them for the first time just above the critical Weizmann number. Here, you can see clearly the elastic wave intensity in the linear log scale plot of the span-wise velocity spectrum compared to the streamwise velocity spectrum EU in the inset with a sharp decay power spectrum. The space-time plot and the time series of wave structure further reveal this behavior. By quantifying the world normal vortices with two independent methods, shown here in green and red, we found a very strong agreement. We also found a clear correlation among three quantities: the friction factor, the world normal vortices, and the elastic intensity across different flow regimes. This shows the important role of the elastic wave in this chaotic flow. They extract energy from the mid-flow and transfer it into the vortex fluctuations, thereby sustaining elastic turbulence. According to the theory, this amplification mechanism only works when elastic wave energy is sufficiently large. But what happens near the onset of the instability when the elastic wave intensity is not yet large enough to sustain the chaos? This becomes our central question. What mechanism replaces the elastic wave amplification process when Weizmann number is very close to the critical Weizmann number? Here is our experimental setup. The flow is pressure-regulated nitrogen gas driven by the pressure-regulated gas. PIV and pressure measurements are done on the streamwise and the span-wise plane, the XZ plane. The control parameter here is Weizmann number from 30 to 6,000, and the Reynolds number correspondingly is pretty small, from 0.005 to 0.9. In this channel, we usually call in our setup is channel 2, with a critical Weizmann number at 150, as you can see from the friction factor and the fluctuations of pressure and fluctuations of velocity versus Weizmann number. Clearly, the critical Weizmann number 150. By suddenly increasing or decreasing the pressure at inlet at time 0 here, we create the jump across the critical Weizmann number 150. We observe just above the critical Weizmann number, the streamwise velocities exhibits such periodic negative velocity spikes compared with the mid-flow. And it's very clearly visible in the streamwise velocity spectrum here. You can see the frequency domain of the velocity. There is a sharp peak here. After noticing the periodical spikes in such streamwise velocity time series, let us further explore what happens to the streamwise and the spanwise velocity spectrum. Here on the left is when the Weizmann number is just above the critical 150, the streamwise velocity spectrum EU versus F exhibit a pronounced peak at the low frequency, as you can tell, followed by a sharp decay at higher frequency. Well, for the span-wise velocity spectrum EW, when it's very close to the critical Weizmann number 150, it's very flat. And it's very pronounced. You can tell from on the right, the linear log plot of EU, is the elastic wave peak is very weak. But when it goes further to a higher Weizmann number, such several thousand, you can see the EW is no longer flat, but it shows a very sharp decay with pronounced elastic wave intensity peak. So this low frequency spikes plus the white noise-like flat spectrum and the weak modulation such elastic waves reminded us of stochastic resonance. The simplest model of stochastic resonance is a particle in a double wall potential. Without noise, the system cannot realize transition between two states, A and B, even after weak periodical forcing. But with added noise, the system can cross the potential barrier, and the nonlinear output is actually amplified by the noise in the presence of the periodical modulation. It is actually a counterintuitive effect. So three key ingredients of the stochastic resonance are a nonlinear system, a noise, and a weak periodical modulation. So you can tell on the right, the noise was added to the signal will enhance the performance of the nonlinear system with a very sharp peak of set frequency. However, a classic stochastic resonance connects naturally to such outward funding. However, a particular type called deterministic stochastic resonance is especially relevant. We call it for short DSR. DSR was first discussed by Anishchenko and colleagues in 1993 in the context of the chaotic nonlinear dynamic system. Our system is also treated as a chaotic nonlinear system as well, so they are very close. They show that the resonance can merge in the quiz hyperbolic system either through parameters variation or by adjusting noise intensity at fixed parameter. DSR occurs when a chaotic attractor interacts with weak periodic signal and external white noise. In the middle column, the resonance arises in the middle column. In the Lorentz model with no noise when D, the noise intensity equals 0, it only has one state trained, one or another or the other. We'll add the noise here. D is set as 1. The system manifests itself as a bistable state, but more like two chaotic attractor at B over 1. Here, B is the one of the control parameter of the Lorentz model. In DSR, resonance arises in this chaotic system without need for the external white noise. Instead, the chaotic attractor itself interacts with the weak periodical signal and the background fluctuations. In our case, the chaotic attractor is represented by the decaying EU, the streamwise velocity spectrum. The weak periodical forcing of the signal is the weak elastic wave, and the background fluctuation is the flat white noise-like spectrum EW at very close to the critical Weizmann number. The negative specs we observed at the beginning are the system's response in this DSR framework. We further examine how DSR varies with Weizmann number and with downstream distance, since it's a convective case. DSR only appears in a limited region of Weizmann number and L over H. L over H is L is the distance from the inlet, and L is the channel height. We found the negative spec intensity. This is the negative spec intensity as the signature to judge the existence of DSR depends. This is the frequency. This is the intensity. The intensity depends non-monotonically on Weizmann number, and there is a clearly threshold in the intensity of the elastic wave. Before this threshold, the span-wise velocity spectrum remained flat with very weak elastic wave intensity. But over this threshold, the span-wise velocity is no longer flat, but with a chaotic decay and significant high elastic wave intensity. Moreover, the closing dependency of the spec frequency and the elastic wave frequency is close dependency scaling relation with Weizmann number show their direct relation, no matter in a manner of subharmonic or harmonic way. Thus, the essential conditions for DSR are first, a power law decay of EU indicating the chaotic state. The second, a flat white noise like EW indicating noise. And the third final one, very weak elastic wave intensity indicating a modulation. This is constant with the theoretical model such as DSR in Lorentz systems as presented in the previous slide. We plotted emergence of DSR in this Weizmann number and L over H from the downstream location phase space. The red cross is at difference is where we found the DSR, and the blue dot is the cases where we didn't find DSR at all. You can see DSR never appears at inlet, since elastic wave have sufficiently large intensity. DSR rapidly, as you can also tell from on the right, this is the elastic intensity on L over H. At inlet, the elastic intensity is very high, so the DSR didn't appear at the inlet. Let's go back on the left. You can see
剩余电量50%已经连。
I'm going to continue. You can see the appearance of the DSR range rapidly grow along the L over H, expanding the Weizmann number range and reach such a constant range until the end until the end of the outlet. On the right, you can also see a similar trend of the fluctuations of velocity, which treated as the inlet perturbation propagation. A rapid decay at first, followed by a slower one. So this cross point near the L over H around 180, also here 100 over 80 around, suggests the velocity fluctuation rather than the L over H is the true control parameter here. So DSR depends on the two true control parameter. One is Weizmann number, the other is the velocity fluctuations level, here noted as the UMS. So to conclude, we report the first observation of deterministic stochastic resonance in fluid dynamics, especially in the chaotic viscoelastic channel flow, and 3 essential conditions for DSR. One is the chaotic flow, noted as the rapid decay of EU. The second is white noise, noted as the flat EW, and the last one is the low amplitude modulation, noted as the low elastic wave intensity. Third, DSR happens upon the instability onset when EU becomes chaotic and EW remains a flat one, and elastic wave amplitude is small, only serving as a periodic modulation source. After elastic wave amplification grows across the threshold, making EW no longer flat, and the amplification mechanism by elastic waves takes over DSR to sustain the chaotic flow state. 4. Velocity fluctuations is another important control parameter here of DSR besides Weizmann number. Thanks for your attention. I would like to thank again the PRF Journal Club Committee for this opportunity. I now welcome questions. Both Victor and I will be happy to answer.
Great. Thank you so much for the very interesting presentation. And as you said, we're going to open the floor to questions. As a reminder, you can just raise your hand and ask your question through the microphone, or just post your question in the chat. One question that I had, Yuke, when I was seeing your presentation, is if you have tried any amplitude equations that might describe this phenomena to apply them to get some insights, like, I don't know, like a Ginsburg-Landau equation or something that might explain this mechanism. What is the state of the art of amplitude equations for this case?
Landau equation is not applicable here because it's transition from laminar to chaotic flow, many modes. Landau described on the transition from one mode to another stable mode, and that's it. Therefore, it's what is here is transition called non-normal mode instability. It occurs in case that linearized equation describes this phenomena. It's non-Hermitian. And that's you have both normal modes and non-normal. Normal modes are stable, and non-normal turns out to be unstable. And that's what's reason for instability. Here, what is surprising is this instability continues, not like hysteretic that in pure Newtonian fluid for large Reynolds. And that's big difference. And for this reason, for many years already, at least 6 years, people could not accept this. And that's the reason. Okay.
Perfect. Makes sense.
You can also tell from this EU streamwise velocity spectrum. You can see before 146, the spectrum is flat, so it's just random noise. It's a laminar flow. But when it reaches 146 here, the spectrum becomes instantly decay. So it excited infinite modes. And some modes are the low frequency, the stochastic resonance performance. Some are the polar decay followed at higher frequency. So there is no such single mode or amplitude equation can predict.
But still, I assume you could have a linearized operator with at least two non-normal modes, some nonlinearity, cubic nonlinearity, and some stochastic forcing. At all of them, they could reproduce the finding. But your argument is that you would need more than one mode for the linearized operator. We have a question in the chat for stochastic resonance, for deterministic stochastic resonance. It seems you need external noise, and thus, from my understanding, you have control over this noise, but this is not the case here. So how is this consistent with the idea behind DSR?
It's in DSR, there are two possibilities. The main possibility in DSR that you have perturbation in the inlet, of course. You have perturbation, you have three condition, actually a chaotic attractor. I'm speaking about model, deterministic model. Chaotic attractor, you have limit cycle inside also of this, and plus you can have outside noise, or you can have noise inside as a result of transition between three different attractors. It described by parameter which is defined the it's called mixing of this different chaotic modes, and in this case, this control parameter, which is responsible for connection of this different modes, critical. Below, you don't need even external noise. Above, you need external noise. And we have, you see this is our model. It's not described completely our complicated system, but probably we have situation with only attractor where noise can change the trajectories. That's it. Inside of this one chaotic attractor, we have transition due to noise, transition for different lines. And that's the reason. Therefore, we cannot describe this analytically so complicated system like ours, or even model. And we compare with very simple, actually, mathematical model. And that's it. Okay.
Perfect. Do these mathematical models capture this ratio of frequencies, that the frequency goes 4 or 5 times, I think, less than the elastic wave frequency? Is that the subharmonic resonance, or?
Yeah, we have connection between, and we show this connection between here. You see, that's dependence of friction factor of frequency of the stochastic resonance as function of Weizmann, and the same you have in case of elastic waves. Therefore, definitely they connect to each other, but the frequency of stochastic resonance smaller between 1 and 5 times. For very small perturbation, we have almost the same frequency. For higher perturbation, we have big difference. And it's the same happens in model. The same.
Very interesting. Ricardo has a question. Ricardo, please go ahead and unmute yourself and ask your question.
Yes, hi. Thank you for your presentation. Could you go back to your slide where you're showing your experimental device, please? I have it's a rather simple question actually, but I just want to confirm. You went over it a little bit fast, so I wasn't able to check. It's just about what the conditions are for the velocity field versus the point-wise velocity. And I was a bit confused as to why the single point velocity measurement is done with a higher magnification than the velocity field one. I would perhaps have thought otherwise.
Here, actually,
okay.
good question. Sorry, I forgot to mention this part because time is limited. Here, we use 4 X objective lengths, both for the single point measurement, for the spectrum analyzed, also for the velocity field. And the second line, velocity field with 0.2 micron particle plus the 20 X objective length is used for the vorticity measurement here. Here, it's only used here because at large scale, we didn't find it. For large scale, I mean the 4x object length, we didn't find the vorticity, but with a 20x object length, after analyzing the velocity field, we got such vorticity. So this 20x object length is only used here. So also in the previous slide, the Strix evolution here and the spectrum, here we use the 4x objective length. So when we measure only small square here, it serves as a single point measurement for a long time series, then we can get a velocity spectrum. If we increase the resolution, we can get almost a cross channel, full width of the channel to show the Strix evolution. The red one is the high velocity Strix compared to the mean flow, and the blue one, the lower one.
And from this slide also, did you ever try using an inlet that doesn't have any bending at all? One might think that you're saying that the URMS is bigger at the inlet, but that's also where you have some curvature in your streamlines, right? And that's something that worries me a little bit. So could someone argue that those fluctuations might be coming from that bending at the inlet? And so have you tried anytime a straight inlet to avoid that?
Actually, in experience, we cannot make the inlet always the same from the pressure containing liquid tank. So you can tell from the left of this panel. Here, case is this flow comes here, and after 2 red corner, it enters the channel. It's a straight one. They all straight, but with 2 red corners. And here is the an array of pillars upstreams. Here we want to reduce the inlet perturbation, so we make the inlet converging. But here we treat it as the 0 position, and after this, they all just a rectangular cross-sectional channel. So there is no.
Yeah, sure, but can you assure that this initial bending is not what is bringing the instability? Can you be sure about that?
It's produced perturbation, and that's what we need. And we can change perturbation by changing this inlet. And that's what we made. The difference between this smooth part and these non-smooth parts about 10 times in amplitude of perturbation. And that's only, we don't use any additional perturbation from outside because we want to get perturbation only flat. It means that a flat power spectra. Therefore, you don't have dependence, it's a white noise, and that's what we need. If it's not white noise, it's working different way. Yes.
Thank you.
Okay. Well, thank you. I think the time is
Thank you for the question.
I have taken too much time. Thank you. Thank you very much.
I see we don't have any other questions, and we've reached the half hour. So join me to thank the speakers once again, and also for the interesting Q&A session. And thanks for your very interesting presentation once again.